core concepts in physiology because it's a law that applies to many different relationships that are important in physiology. Some of them we've already looked at, and some of them are important in cell metabolism. So in this video, we'll first introduce the law of mass action. So what is it? And I'm going to warn you right away, we start taking a mathematical approach to explain the law of mass action. But what is most important for us is to then apply this law to physiological examples. Specifically, we'll look at how it applies to chemical reaction, enzyme substrate binding, and receptor ligand binding relationships. So by the end of this video, you should first be able to explain the law of mass action in your own words. You don't have to detail the mathematical relationships, but you do have to be able to explain it in your own words and then be able to give examples within these three categories: chemical reaction, enzyme substrate binding, and receptor ligand binding. So to introduce this law of mass action, imagine these two different beakers with different amount of water. So on the left, we have a beaker that has lots of water, and on the right-hand side, we have a beaker that has little water. And now imagine that these beakers are connected by a tube. If there was a tube between the two beakers, you know that the water from beaker on the left would flow into the beaker on the right. But would the water flow this way forever? And intuitively, most of us would say no. At some point, there would be equal amount of water in both beakers, and the water would stop flowing. So remember this analogy as we move forward explaining the law of mass action. The other concept that I want to review before we get into the law of mass action is the concept of dynamic equilibrium. And we first introduced it when we looked at diffusion. Let's take the example at the top here. We have two beakers, A and B, that are separated by a semi-permeable membrane. We saw many of those examples when we discussed diffusion. In beaker A, we have a solution of 4 millimolar of glucose, and in beaker B, we have a solution of 10 millimolar of glucose. So before diffusion happens, this is a state of disequilibrium because the concentration on either side of the membrane is different. We now know that diffusion is going to occur from an area of high concentration to an area of low concentration, so glucose will move from B to A via diffusion. So once diffusion has had time to happen, now we have a state of equilibrium, where the concentration in A is the same as the concentration in B. It's 7 millimolar on both sides of the membrane. At this point, the concentration in A and B no longer changes. It's going to remain constant at 7 millimolar. However, the molecules keep moving. That's why we call it dynamic equilibrium. Dynamic means movement. So how is it possible that the molecules keep moving, but the concentrations don't change? It just means that for every molecule of glucose that crosses from A to B, there is another molecule of glucose that crosses from B to A. So in other words, the rate of transport in one direction is exactly the same as the rate of transport in the other direction. So the molecules move, but it doesn't result in a net change in concentration. So this should be a reminder of this concept of dynamic equilibrium, and you'll see that this will become relevant as we move forward with our law of mass action. So here's our definition of the law of mass action. It states that for a reaction at equilibrium, and really we should add dynamic equilibrium, the ratio of the products to reactants is always the same. So let's define a few terms here. So here we're looking at this hypothetical chemical reaction where A plus B makes C plus D. But you'll notice here that the arrows are in both directions. And that means that this is a reversible reaction, meaning that yes, A plus B can make C plus D, But C plus D can also be used to make A plus B. Now, the large majority of chemical reactions that take place in the human body are reversible reactions, which means that the large majority of chemical reactions in the human body do obey the law of mass action. That's why it's such an important concept to understand. The two other concepts we need to be familiar with are the words reactants and products. So let's start with reactants. Reactants are the molecules that are on the left side of a chemical equation. Sometimes people will call them substrates as well. And products are the molecules that are on the right side of the chemical reaction. So in this reaction, A plus B makes C plus D. At equilibrium, or at dynamic equilibrium, the concentrations of A, B, C, and D do not change. Is this because the reaction is stopped? Absolutely not. The concentrations of the reactants and the products don't change, but that's because the rate of the forward reaction is exactly equal to the rate of the reverse reaction. So let's look at this at the bottom here. The forward reaction is when A plus B makes C plus D. The reverse reaction is when C plus D make A plus B. And at equilibrium, these two reactions have an equal rate, which means that for every one molecule of A plus B that's converted to C plus D, there's also one molecule of C and D that are converted to A and B. So the reaction still keeps going, but the actual concentration of each of the reactants and each of the products do not change. Hopefully you can see that this concept is very similar to the dynamic equilibrium that we discussed when we discussed diffusion. It's the same concept, just applied to different process. So this is one way to explain the law of mass action using primarily words. Now, let's see how this looks from a mathematical perspective. So let's first go back to the definition. For a reaction at equilibrium, the ratio, I'm going to highlight here, ratio of the products to reactants is always the same. Remember that when you see the word ratio, it always means a division. So it's going to be something over or divided by another number. So the ratio of the products to the reactants is constant or is always the same. And this is what we see here. So the concentration of C times the concentration of D, these are our products. So products here at the top, over the concentration of A times the concentration of B, which are our reactants, equals a constant. And we call this constant the equilibrium constant, or KEQ. A simpler way of writing this out is here. So using C and D in square brackets just means the concentration of, and same here. So the concentration of C times the concentration of D over the concentration of A times the concentration of B equals this equilibrium constant. So this slide and the previous slide do convey the same message. It's just two ways of looking at the same concept. One is more using words, the other one is more using mathematical equations. So the real question that will become really important in physiology and in this course is what happens with the law of mass action when equilibrium is disturbed. So let's see if we can answer this question. First of all, here's our step one. That's when a reaction is at equilibrium. So you see here that we represent the reactants and the products basically on a scale. Remember that A and B are our reactants and C and D are our products. And this cartoon depicts what we just described, where at equilibrium, the rate of the forward reaction, R1 here, is equal to the rate of the reverse reaction. And as such, if you divide the product by the reactant, it gives you your equilibrium constant, and that's what indicates that our reaction is at equilibrium. Now let's say that equilibrium is disturbed by adding more product. So here you can see that our products represented in blue, so that's A times B has been increased. And as such, the reaction is no longer at equilibrium. If you were to do the ratio between the products and the reactant, the ratio would no longer be at that equilibrium constant. So how can the system bring this reaction back to equilibrium? It will do so always by either increasing the rate of the forward reaction or increasing the rate of the reverse reaction. Let's think about this logically. In this case, to reestablish the equilibrium, we need to get rid of some of the reactants. How do we do this? The system increases the rate of the forward reaction. So I'm going to make a thicker arrow here. It increases the rate of the forward reaction, and that will bring the reactants product down, as well as increasing the products a little bit, and we'll be back to equilibrium. So let's keep going through our cartoons here to see if that's what happens. Indeed, so in step 3, we see the reaction rate increases. So we see this thicker arrow for the forward reaction. In other words, the system starts converting more A and B into C and D. And in our fourth and final step, we see that this dynamic equilibrium has been restored. So now let's compare our reaction at equilibrium in step 1 with our reaction at equilibrium in step 4. You can see that the amount of reactants is not the same. It's greater in step 4 than it was in step 1. Same thing with our amount of products. It's greater in step 4 than it is in step 1. How is this possible? Remember that the law of mass action tells us that it's not the concentration themselves that are constant, it's the ratio of concentrations. Let me give you here a simple example. Let's say that at step 1, we have 2 of the reactants and 4 of the products. We know that TEQ is equal to the products over the reactants, which would mean 4 divided by 2, and our ratio is 2. Now, let's see what might happen at step 4. So at step 4, our reactants are greater than at step 1. Let's say they're now at 3, but our products are also greater. So let's say that they're at 6 now. Let's do the same math. Products over reactants is 6 divided by 3, and we still have an equilibrium constant of 2. So here the take-home message. The law of mass action tells us that when equilibrium is disturbed, like it was here in step 2, a system adapts either by increasing the forward reaction or increasing the reverse reaction in order to reestablish this dynamic equilibrium. Basically, in order to bring back that system to the equilibrium constant. Now let's look at a few examples of that. So we saw earlier in this unit that pyruvate can be converted to lactate when conditions have limiting oxygen. We also saw that pyruvate can be converted to acetyl-CoA when there's lots of oxygen available. Now, for the purpose of this example, we're really focusing on the conversion of pyruvate to lactate. And the important thing here is that this is a reversible reaction. So we haven't talked about it much, but pyruvate can be converted to lactate, but lactate can also be converted to pyruvate, making this a reversible reaction. Here is our chemical equations for pyruvate and lactate. So pyruvate plus NADH plus H plus make lactate and NAD plus. Or lactate and NAD plus make pyruvate plus NADH plus H plus. So pyruvate and NADH are our reactants, while lactate and NAD plus are our products. So what I want us to walk through here is every single example of how the equilibrium can be disturbed here. And we'll first look at the direct effect. So what is the initial disturbance and how will the reaction rates change in order to restore our dynamic equilibrium? So our first example is when pyruvate concentration increases. So the direct effect is that we have an increase in pyruvate concentration. How is the system going to restore the equilibrium? In this case, we want to get rid of some of the extra pyruvate and convert it to lactate. So the reaction that will help us with that is the forward reaction. So here, the compensation is to increase the rate of the forward reaction. Let's look at the opposite example. What happens when pyruvate concentration decreases in this? So the first effect, the direct effect, is a decrease in pyruvate concentration. So now we have an imbalance where lactate is greater than pyruvate. So to restore this, the system must convert lactate back into pyruvate to get back to that equilibrium constant. How can the system do this? By increasing the rate of the reverse reaction. So here we increase the rate of the reverse reaction. Let's look at two more examples to make sure that our understanding of this is solid. What happens when the disturbances affect lactate? So now we look at an increase in lactate concentration. So when lactate concentration increases in the system must restore equilibrium by converting lactate back to pyruvate. How does it do this? By increasing the rate of the reverse reaction. So increasing the rate of reverse reaction. So at the end of this, remember that lactate will still be increased a little, but so will pyruvate. So the concentration of lactate by itself is still higher than before the disturbance. The concentration of pyruvate by itself is still greater than before the disturbance, but the ratio is kept the same. And that's what's important with our law of mass action. Our final example is when lactate decreases. So here, if lactate decreases, our equilibrium is shifted so that there's too much reactant, too much pyruvate for the amount of lactate. So the solution is to convert pyruvate to lactate. How does the system do this? By increasing the rate of the forward reaction. So here is the first example of how the law of mass action applies to chemical reaction. And as we move forward through cell metabolism unit, as well as next semester, we will use this law of mass action over and over again to understand how the body maintains homeostasis. Now, the law of mass action does not only apply to chemical reaction. It actually applies to any protein binding interactions. And we've already discussed a few of those systems. So another example, the law of mass action, is how we can regulate the enzyme substrate binding. So I want to bring your attention at the top here. This is our enzyme. And if you remember, the function of an enzyme is to bind substrate, here substrate 1 and substrate 2, in order to facilitate chemical reaction. So what we've looked at so far with the law of mass action was looking at the concentration of reactants and the concentrations of products. Now, if you change that to enzyme and substrate, the relationship here is that the ratio between the bound enzyme and substrate over the unbound enzyme and substrate is also constant. That's our equilibrium constant right here. In other words, the ratio between how much enzyme is bound to a substrate and how much enzyme is not bound to a substrate is always constant. And that's what we see here. It is the same law of mass action equation, but instead of having products and reactants, we have enzyme and substrate. Bound enzyme and substrate, unbound enzyme and substrate. So how does this affect physiology? So think about what would happen in a system if the concentration of enzymes increase. Let's try to draw this. So on the left-hand side here, we're gonna draw, let's say, 3 enzymes, and one of them is bound by a substrate, and the other substrates are unbound. Now let's see what happens when the concentration of enzyme is increased. Instead of having 3 here, we'll have 4 different enzymes. So in order to keep that ratio of bound to unbound enzyme constant, there will be more substrate binding to the enzyme. And that means that this reaction rate would increase because more enzyme molecules would be active. And the same would work for substrate. If the concentration of substrate increased, then more of it would bind to enzymes. So the take-home message here is it really doesn't matter whether the disturbance comes from increasing or decreasing the concentration of enzyme or increasing or decreasing the concentration of substrate. If you change one component of the system, it has a chain effect that will then also alter the other component. So here, going back to this example, we altered the amount of enzymes. We went from 3 enzymes to 4 molecules of enzyme. And as a result, this altered the amount of substrate that was bound to the enzyme. And that's how the system restored dynamic equilibrium. Let's look at our final example. So earlier in this course, we looked at cell communication, and we spent a lot of time discussing receptor-ligand binding relationship. Now, this relationship also obeys the law of mass action. At equilibrium, the ratio of bound to unbound components remains constant. So similarly here, bound receptor and ligand over unbound receptor and unbound ligand always equals the equilibrium constant when the system's at equilibrium. So this is very similar to what we just saw with the enzyme. So here we have our plasma membrane of our cell that expresses 2 receptors. Our bloodstream is here, and it has a certain concentration of ligand inside the blood. In this first situation, you can see that only one receptor is occupied by a ligand, and the other receptor is not occupied by a ligand. Now, what happens to maintain that equilibrium if the cell, through exocytosis, now expresses 1, 2, 3, 4 receptors instead of 2? Based on the example that we've just discussed, we should know now we would have more ligand now binding to the receptors because we always need to keep that ratio of bound to unbound receptor constant. So I hope this helped introduce you to the law of mass action. Most importantly, we need to understand how this applies to the 3 types of example we just reviewed: chemical reaction, enzyme substrate binding, and receptor ligand binding. And you'll see that although it's the first time that we use the law of mass action in this course, it is certainly not the last time that we'll refer to it. So if you have any questions, never hesitate to reach out to us at phyl10xx@dow.ca.